Support for this podcast comes from the Institute on Aging, providing integrated dementia and home care with customizing care plans to meet the specific needs of aging adults in their homes. Learn more at ioaging.org.
From KQED.
From KQED Public Radio in San Francisco, I'm Mina Kim. Coming up on Forum, journalist Joe Kahane makes the case for talking to strangers. Psychological research has shown even brief interactions can enhance feelings of happiness and belonging. According to Kahane, we get his thoughts on exercising our pandemic-atrophied social skills. First, though, we'll check in on a major breakthrough by California scientists who found a way to tap into the brain of a man who is unable to speak and transmit the words he wants to say to a screen. The technology could help the thousands of people each year who lose speech from stroke, accident, or disease. That's all next on Forum. Join us. This is Forum. I'm Mina Kim. In what's been called a major achievement, scientists at UC San Francisco have developed an implant that can read the brain signals of a man who is paralyzed and unable to speak and translate those signals to text on a screen. Two of those researchers join me now. Edward Chang is professor of neurosurgery at UCSF. He also co-directs the Center for Neural Engineering and Prosthesis at UC Berkeley and UCSF. Welcome, Edward Chang.
Hi, good morning.
Also, David Moses is with us, a postdoctoral engineer at UC San Francisco. Welcome to Forum, David Moses.
Hi, nice to meet you.
Nice to meet you as well. And if you, our listeners, want to join with comments or questions, as always, you can post them on Twitter or Facebook, email us forum@kqed.org, or call 866-733-6786. Well, Dr. Edward Chang, this is truly astounding. I mean, technology that can decode words and full sentences directly from the brain signals of someone who has been paralyzed for years and cannot speak. First, what did it feel like to realize your foundational work made this possible?
Well, this is a really complicated project, and we really didn't take any assumptions going to this, but it really relied on over a decade's worth of research trying to understand how a particular part of the brain called the sensory motor cortex controls the muscles of our vocal tract, meaning like the lips, the jaw, the larynx, when we speak. And it's really precisely coordinated kind of movement that gives rise to all of the different consonants and vowels in English. And we've been studying that very intensely in people who speak normally for the past decade. And once we figured out a lot about how that neural code works for expressing different speech sounds of English, we wanted to see if we could use that knowledge to help someone to decode what they wanted to say after they've suffered a stroke, for example, and lost the ability to speak.
And David Moses, how are you able to read the brain signals? What is the implant exactly?
So the implant is a sheet of 128 electrodes, so sensors that are placed on the surface of the brain that Dr. Chang implanted with his study participant. And from this, it kind of records electrical activity as the participant is attempting to speak. And we use that information offline using machine learning, advanced computational models to try and detect subtle patterns in the electrical activity and relate those to the words that the participant was attempting to say.
I see. So like an algorithm translates that brain activity in real time, basically.
Yes, that's exactly right.
And Dr. Chang, you were saying that you are tapping into the part of the brain where there are signals controlling the vocal tract. So basically, your study participant who wanted to remain anonymous really has to be trying to say or attempting and intending to say something. This sort of implant is not reading his mind or displaying thoughts and text that he doesn't want people to see?
Mina, thanks for clarifying that. That's exactly right. This is not a device that was designed to read his thoughts or his feelings or emotions. It's literally what he's trying to say through his mouth, but can't because of the injury and stroke that he had before.
But it sounds like what you discovered was that even if he hadn't necessarily been using those muscles, the brain still knew what to do.
Yeah, that's exactly right. And I would have to say that that was one of the biggest challenges that we encountered in this project, was just not knowing ahead of time whether or not that part of the brain would still work after 15 years of not speaking. The participant in this trial, and it's really just the starting point, he's the first participant, and this was the first project as part of this trial, lost the ability to speak 15 years ago after a brainstem stroke. And the brainstem is a part of the nervous system that connects the brain to the spinal cord and the nerves that go out to the vocal tract. And so after that accident, he was severely paralyzed and hasn't really had the ability to speak any fluent words for the past 15 years. So that was a really big, I would say, challenge for us to understand if this was still even possible.
And sure enough, it was. We're talking with Edward Chang, professor of neurosurgery at UCSF, and David Moses, a postdoctoral engineer at UCSF. We're talking about new technology that can translate brain signals into words on a screen and a potential breakthrough for those unable to speak. David Moses, how was the man communicating before, and how much faster is this process of reading the brain signals?
Mina, thanks for asking that. Before we started the study, he uses, and even now in his daily life, he uses residual head movements to type out intended messages letter by letter with through assistive technology. So, for example, he has very slight neck and head movements that he still has even after his paralysis, and he uses those to type out messages using like a pointer that's attached to a baseball cap onto like a tactile screen. And so this is obviously, it's very important for him to be able to use this kind of technology in his daily life. But it is, as you might imagine, pretty slow and effortful and tedious to type out everything that he wants to say. So right now with this technology in the study, that's just the starting point. We have about, 15 to 18 words per minute that we can get through his brain activity as he's trying to say sentences. But we hope that with further research and development, we can approach the natural rate of speech, which is kind of the fastest way that people can communicate, which is around 150 words per minute or even higher sometimes.
Yeah. And David Moses, what has been his reaction to this technology and the role he played in developing it with you through his involvement?
Yeah, I mean, I cannot overstate how amazing and remarkable this person is to have, when he signed up for the study, he knew that the technology might not immediately benefit him because it's very exploratory. I mean, it was possible that none of it would have even worked at all. I mean, he is truly a pioneer for this. He's the first human to ever accomplish this. And so I think through his, sacrifices and all the time that he spends working with us, when he was able to finally see that the technology was working and that what he was trying to say was appearing on the screen successfully, he was extremely excited. His face lit up. And I think that it's very fulfilling to see all of his effort and determination, lead to something that will help this technology to eventually help other people.
So, Dr. Edward Chang, where does this go from here? How do you see the promise of this in terms of helping other people, as David Moses says, and how soon you could get there?
Well, we're very optimistic. This is just the starting point, and there's a lot of room for improvement. We're thinking about ways to improve the hardware, the device that was implanted, and how to make that something that may be easier to do in the future, higher resolution, wireless. There's so many things that we can improve in terms of the hardware. And then same thing goes for the software, really just the algorithms that were used to decode those really complex and subtle brain signals into words also have a lot of room for improvement. And I think that, again, this is just the starting point. We also need to know basically if this is something that can help other people in similar conditions. There's other situations, neurological conditions that result in the loss of ability to speak. And we'd like to really understand, how much this can generalize to other people to be more broadly helpful to a larger population.
Dr. Chang, I was struck by something you told the New York Times, which is that in the future, this technology could be used to read what people are thinking. And you said something about how that raises really important ethical questions about this kind of technology. Is that a concern for you? There's always concerns that technology can be misused, especially one as powerful as this that can read brain signals, making sure that it's what people want to share, for example.
Yeah, thank you for asking about that. I am concerned about that. I don't think that we're close to that point yet, but the fact that we can essentially translate brain signals related to what someone wants to say, in theory, suggests that more powerful forms of this will be developed in the future and may not even apply to people who are in medical conditions, like to a more consumer population or general population that's otherwise healthy. And so I think we need to think about these kind of implications now, and we need to have more conversations about that and really just understand where we want to draw the line and make sure that it stays in a way that is helpful and ethical and really grounded in where the needs are.
Meantime, David Moses, what has working on this project and working with Dr. Chang just taught you about the importance of communication in any form to the human condition, I guess?
Yeah, I would love to talk about that. It's been a long journey for me personally because I got my PhD in Dr. Chang's lab as well. And I started by working with people who are able to speak naturally and they don't have speech deficits. And so it was pretty easy for me to just focus on the research and the science questions and developing new technologies. But as part of this clinical trial that this new work is part of, it's been extremely eye-opening for me to see what it's like for people who are not able to communicate, who are not able to speak. And I think it's really easy to take for granted, but speech is an incredibly complex process, and it's kind of fundamental to who we are to some degree. And I think that a long-term goal of trying to restore the ability to speak to those who have lost it, is very fulfilling personally.
Well, thank you for your work. David Moses, postdoctoral engineer at UCSF, and thank you, Dr. Edward Chang, professor of neurosurgery at UCSF, who also co-directs the Center for Neural Engineering and Prosthesis at UC Berkeley and UCSF. We've been talking about their new technology that can translate brain signals into words on a screen in a potential breakthrough for those unable to speak. We'll have more Forum after the break. I'm Mina Kim.